Something that I actually won't spend a lot of time on. And then I want to start to talk about support vector machines. And support vector machines is the learning algorithm, is the supervised learning algorithm that many people consider the most effective off-the-shelf supervised learning algorithm. That point of view is debatable, but there are many people that hold that point of view. And we'll start discussing that today. And this will actually take us a few lectures to complete. So let's talk about naive Bayes. To recap from the previous lecture, I started off describing spam classification as the motivating example for naive Bayes, in which we would create feature vectors like these, right, that correspond to words in a dictionary. And so, based on what words appear in a piece of email, we're represented as a feature vector with ones and zeros in the corresponding places. And naive Bayes was a generative learning algorithm. And by that I mean is an algorithm in which we model P of x given y. And for naive Bayes specifically, we modeled it as product from I equals 1 to n, P of xi given y. And also we modeled P of y. And then we use Bayes' rule, right, to combine these two together. And so our predictions, when you're given a new piece of email, you want to tell the spam or not spam, you predict argmax over y, P of y given x, which by Bayes' rule is argmax over y, P of x given y, times P of y. Okay? So this is naive Bayes. And just to draw attention to two things. One is that in this model, each of our features were 0, 1, so indicating whether different words appear. And the length of the feature vector was, so the length n of the feature vector was, the number of words in the dictionary. So it might be, for instance, on the order of 50,000 words, say. What I want to do now is describe two variations on this algorithm. The first one is the simpler one, which is just a generalization to if xi takes on more values. So, one of the things that's commonly done is to apply naive Bayes to problems where some of these features xi takes on k values rather than just 2 values. And in that case, you actually build a very similar model where P of x given y is really the same thing, right? Where now these are going to be multinomial probabilities rather than Bernoulli's, because the xi's can maybe take on up to k values. It turns out one situation where this arises very commonly is if you have a feature that's actually continuous valued, and you choose to discretize it. You choose to take a continuous value feature and discretize it into a finite set of k values. And so as a concrete example, if you remember our very first supervised learning problem of predicting the price of houses. If you have a classification problem on these houses, so based on features of a house, if you want to predict whether or not the house will be sold in the next 6 months, say, that's a classification problem. If you want to use naive Bayes, then given a continuous value feature, like the living area, one pretty common thing to do would be to take the continuous value living area and just discretize it into a few discrete buckets. And so depending on whether the living area of the house is less than 500 square feet or between 1,000 and 1,500 square feet and so on, or whether it's greater than 2,000 square feet, you choose the value of the corresponding feature xi to be 1, 2, 3, or 4. Okay? So that was the first variation or generalization of naive Bayes I want to talk about. I just check. Are there questions about this? Okay, cool. And so it turns out in practice, it's fairly common to use about 10 buckets to discretize a continuous value feature. I drew 4 here only to save on writing. The second and so final variation I want to talk about for naive Bayes is a variation that's specific to classifying text documents, or more generally for classifying sequences. So text document, like a piece of email, you can think of as a sequence of words. And you can apply this little model I'm about to describe to classifying other sequences as well. But let me just focus on text. And here's the idea. So the naive Bayes algorithm, as I've described it so far, right, given a piece of email, we were representing it using this binary vector value representation. And one of the things that this loses, for instance, is the number of times that different words appear. Right? So for example, if some word appears a lot of times, if you see the word buy a lot of times, if you see the word, I don't know, Viagra seems to be a common email example. If you see the word Viagra a ton of times in email, it's more likely to be spam than if it appears, I guess, only once. Even once, I guess, is enough. So let me describe a different, what's called an event model for naive Bayes that will take into account the number of times a word appears in an email. And to give this previous model a name as well, this particular model for text classification is called the multivariate Bernoulli event model. It's not a great name. Don't worry about what the name means. It refers to the fact that there are multiple Bernoulli random variables, but it's really don't worry about what the name means. In contrast, what I want to do now is describe a different representation for email in terms of the feature vector, and this is called the multinomial event model. And again, there is a rationale behind the name, but it's slightly cryptic, so don't worry about why it's called the multinomial event model. So just call it that. And here's what we're going to do. Given a piece of email, I'm going to represent my email as a feature vector. And so my ith training example, xi, will be a feature vector xi subscript 1, xi subscript 2, comma, xi subscript ni, where ni is equal to the number of words in this email, right? So if one of my training examples is an email with 300 words in it, then I represent this email via feature vector with 300 elements, and each of these elements of the feature vector, let me just write this as x subscript j. These will be an index into my dictionary. Okay, and so if my dictionary has 50,000 words, then each position in my feature vector will be a variable that takes on one of 50,000 possible values corresponding to corresponding to what word appeared in the jth position of my email. Okay, so in other words, I'm going to take all the words in my email and create a feature vector that just says which word in my dictionary was each word in the email. Okay, so different definition of ni now. Ni now varies and is different for every training example, and these xj's now indexed into the dictionary. These the components of the feature vector are no longer binary random variables. They're these indices in the dictionary and take on a much larger set of values. And so our generative model for this will be that the joint distribution over x and y will be that, where again n is now the length of the email. Right? So the way to think about this formula is you imagine that there was some probability distribution over emails. There's some random distribution that generated emails, and that process proceeds as follows. First, y is chosen. First, the class label is someone going to send you spam email or not spam emails is chosen first. Right? And so first y, the random variable y, the class label, spam or not spam is generated. And then having decided whether to send you spam or not spam, someone iterates over all 300 positions of the email, right? All 300 words that they're going to compose in this email, and will generate words from some distribution that depends on whether they chose to send you spam or not spam. So if they send you spam, they'll send you words. They'll tend to generate words like buy and Viagra and whatever, discount, sale, whatever. And if someone chose to send you not spam, then they'll send you the more normal words you get in an email. Okay. So just careful, right? Xi here has a very different definition from the previous event model, and n has very different definition from the previous event model. And so the parameters of this model are, let's see, phi subscript k given y equals 1, which is the probability that, conditioned on someone deciding to send you spam, what's the probability that the next word they choose to email you in their spam email is going to be word k. And similarly, so same thing. Well, I'll just write it out, I guess. And phi y, which is same as before. Okay, so these are the parameters of the model. And given a training set, you can work out the maximum likelihood estimates of the parameters. So the maximum likelihood estimate of the parameters will be equal to, and now I'm going to write one of these big indicator function things again. It'll be a sum over your training set. Indicator, whether that was spam times sum over all the words in that email, where n subscript I is the number of words in email I in your training set, times indicator xij sk times ni. Okay, so the numerator says sum over all your emails and take into account all the emails that had class label 1, take into account only all the emails that were spam. If y equals 0, then this is 0 and this would go away. And then times sum over all the words in your spam email and count up the number of times you observed word k in your spam emails. So in other words, the numerator is look at all the spam emails in your training set and count up the total number of times the word k appeared in this email. The denominator then is sum over our entire training set of whenever one of your examples of spam, sum up the length of that spam email. And so the denominator is the total length of all the spam emails in your training set. And so the ratio is just out of all your spam emails, what is the fraction of words in all your spam emails that were word k? And that's the estimate for the probability of the next piece of spam mail generating the word k in any given position. Okay. And at the end of the previous lecture, I talked about Laplace smoothing. And so when you do that as well, you add 1 to the numerator and k to the denominator. And this is the Laplace smoothed estimate of this parameter. Okay, and similarly, you do the same thing for, and you can work out the estimates for the other parameters yourself. Okay, so it's very similar. Yeah.
I'm sorry, on the right board, on the top, I was just wondering what the x sub I is and what the n is.
Right. Okay. So in this second event model, the definition for xi and definition for n are different, right? So here, well, this is for one example, xy. So here, n is the number of words in in a given email, right? And if it's the I email, it's subscripting this n subscript I. And so n will be different for different training examples. And here, xi will be, you know, these values from 1 to 50,000. And xi is essentially the identity of the I word in a given piece of email. Okay, so that's why this is looping, or this is a product over all the different words of your email of the probability of the I word in your email, conditional on y. Yeah. Actually, you know what? I apologize. I just realized I overloaded notation. Right. Maybe I shouldn't have used k here. Let me use a different alphabet and see if that makes sense. Does that make sense? Oh, you know what? I'm sorry. You're absolutely right. Thank you. Right. So this in Laplace moving, that shouldn't be k. This should be 50,000. If you have 50,000 words in your dictionary. Yeah, thanks. Right. I stole notation from the previous lecture and then translated it appropriately. So Laplace moving, right. This is the number of possible values that the random variable xi can take on. Cool. Can you just raise your hand if this makes sense? Yeah, okay. Cool. Some of you. Are there more questions about this?
For Laplace moving, the denominator, the plus k, was the number of values that y could take.
Yeah, and let's see. So Laplace moving is a method to give you sort of hopefully better estimates of the probability distribution over a multinomial. And so, was I using x or y in the previous lecture? So if you're trying to estimate the probability over a multinomial, I think x and y are different. I think, was it x or y? I think it was x actually. Well, oh, I see. Right. I think I was using a different definition for the random variable y. But when suppose you have a multinomial random variable, x, which takes on let's use a different alphabet. Suppose you have a multinomial random variable x, which takes on L different values. Then the maximum likelihood estimate for for the probability of x, p of x equals k, will be equal to, right, the number of observations the maximum likelihood estimate for the probability of x being equal to k will be the number of observations of x equals k divided by the total number of observations of x. Okay, so that's the maximum likelihood estimate. And to add Laplace moving to this, you sort of add 1 to the numerator and you add L to the denominator, where L is the number of possible values that x can take on. So in this case, this is a probability that x equals k, and x can take on 50,000 values. If 50,000 is the length of your dictionary, it may be something else, but that's why I add 50,000 as a denominator. What other questions? Yeah.
Is there a specific definition for a maximum likelihood estimation of a parameter? We've talked about it a couple times, and all the examples make sense, but I don't know what the general formula for it is.
I see. Yeah, right. So the definition for maximum likelihood. So the question is, what's the definition for maximum likelihood estimate? so actually, in today's lecture and the previous lecture, when I talked about Gaussian discriminant analysis, I was sort of throwing out the maximum likelihood estimates on the board without proving them. The way to actually work this out is to actually write down the likelihood. Actually, well. So the way to figure out all of these maximum likelihood estimates is to write down the likelihood of the parameters. Phi k given y equals 0, phi y, right? And so given a training set, the likelihood, I guess I'm actually writing the log likelihood, will be the log of the product of I equals 1 to m, p of xi comma yi, parameterized by these things. Okay. Where p of xi comma yi, right, this is given by ni of xij given yi, parameterized by, well, I'll just drop the parameters to write this more simply. Let's put it in. You're applying it to the specific case, to the specific of text classification. One of the reasons that's hypothesized for this is that the second model, the multinomial event model, takes into account the number of times a word appears in a document, whereas the formal model doesn't. I said in truth, that it actually turns out not to be completely understood why the latter model does better than the former one for text classification. And so researchers are still debating about it a bit. But if you ever have a text classification problem, naive Bayes classifier is probably not by far the best learning algorithm out there, but is relatively straightforward to implement and is a very good first algorithm to try if you have a text classification problem. Okay, that's a good question. Yeah.
So the second model is still position invariant, right? It doesn't actually care whether words are relative to each other.
Yep.
And I mean, I assume that like Markov models, they do have that information, and does that usually do better if you have enough data?
Yeah. So the question is the second model, right? Second model, the multinomial event model, actually doesn't care about the ordering of the words. You can shuffle all the words in the email, and it does exactly the same thing. So in natural language processing, this model actually has another name. It's called the unigram model in natural language processing. And there are some other models like so say higher order Markov models that take into account some of the ordering of the words. It turns out that for text classification, the models like the bigram models, the trigram models, I believe they do only very slightly better, if at all. But that's when you're applying them to text classification. Okay. All right. So the next thing I want to talk about is to start to get into discussion of nonlinear classifiers. So it turns out, well, and so the very first classification algorithm we talked about was logistic regression, which had the following form for hypothesis. And you can think of this as predicting 1 when this estimated probability is greater than or equal to 0.5, and predicting 0, right, when when this is less than 0.5. And given a training set, right, logistic regression will maybe do gradient descent or something, or use Newton's method to find a straight line that reasonably separates the positive and negative classes. But sometimes the data set just can't be separated by a straight line. So is there an algorithm that will let you start to learn these sorts of nonlinear decision boundaries? And so how do you go about getting a nonlinear classifier? And by the way, one cool result is that, remember I said, when we talked about generative learning algorithms, I said that if you assume y given x is exponential family, right, with parameter eta, and if you build a generative learning algorithm using this, right, it goes 1, if this is eta 1, this is exponential family with natural parameter eta 0, right? I think when we talked about Gaussian discriminant analysis, I said that if this holds true, then you end up with a logistic posterior. It actually turns out that the naive Bayes model actually falls into this as well. So the naive Bayes model actually falls into this exponential family as well. And therefore, under the naive Bayes model, you're actually using this sort of linear classifier as well. Okay. So the question is, how can we start to get nonlinear classifiers? And I'm going to talk about one method today, which is I'm just going to talk about it very briefly, which is taking a simpler algorithm like logistic regression and using it to build up to more complex nonlinear classifiers. Okay. So to motivate this discussion, I'm going to use a little picture. Let's see. So suppose you have features x1, x2, and x3. And so by convention, I'm going to follow our early convention that x0 is set to 1. And so I'm going to use a little diagram like this to denote a logistic regression unit. Okay, so think of a little picture like this, this little circle as denoting a computation node that takes as input, several features, and then outputs another number that's x subscript theta of x, given by a sigmoid function. And so this little computational unit, let's see. I'm just trying to think, okay, how do I keep you guys entertained while we're waiting for the video to come on? Well, let me say a few more things about neural networks. So it turns out that when you write out a quadratic cost function, like I wrote down on the chalkboard just now, it turns out that unlike logistic regression, that will almost always correspond to a non-convex optimization problem. And so, whereas for logistic regression, if you run gradient descent or Newton's method or whatever, you converge the global optima. This is not true for neural networks. In general, there are lots of local optima, and it's sort of a problem. Multiple digits. That's kind of cool. All right. So, just for fun, let me show you one more video, which was, let's see, this is another video from the video series, The Machine That Changed the World, which was produced by I'm actually going to start off by describing yet another class of linear classifiers with linear decision boundaries, and only be later, sort of in the next lecture or the one after that, that will then take the support vector machines idea and sort of do some clever things to it to make it work very well to generate non-linear decision boundaries as well. Okay, but we'll actually start by talking about linear classifiers a little bit more. And to do that, I want to convey two intuitions about classification. One is, you think about logistic regression, right? We had this logistic function that was outputting the probability that y equals 1. And it crosses this line at 0. So when you run logistic regression, I want you to think of it as an algorithm that computes theta transpose x, and then it predicts 1, right? If and only if theta transpose x is greater than 0, right? IFF stands for if and only if, right? It means the same thing as a double implication. And it predicts 0 if and only if theta transpose x is less than 0, say. Okay? So if it's the case that theta transpose x is much greater than 0, the double greater than sign means is a much greater than, right? So if theta transpose x is much greater than 0, then we think of that as a very confident prediction that y is equal to 1, right? If theta transpose x is much greater than 0, then we're going to predict 1, and moreover, we're very confident it's 1. And the picture for that is, if theta transpose x is way out here, then we're estimating that the probability of y being equal to 1 on the sigmoid function will be very close to 1. And in the same way, if theta transpose x is much less than 0, then we're very confident that y is equal to 0. So, won't it be nice, so when we fit logistic regression or some of the classifier to training set, then so won't it be nice if, right, for all I such that y is equal to 1, we have theta transpose xi is much greater than 0, and for all I such that y is equal to 0, we have theta transpose xi is much less than 0. Okay, so won't it be nice if this is true? That for all that essentially, if for our training set we can find parameters theta, so that our learning algorithm not only makes correct classifications on all the examples in the training set, but further, it sort of is very confident about all of its correct classifications. So this is the first intuition that I want you to have, and we'll come back to this first intuition in a second when we talk about functional margins. Okay, we'll define this later. The second intuition that I want to convey it turns out for the rest of today's lecture, I'm going to assume that the training set is linearly separable. Okay, so by that I mean for the rest of today's lecture, I'm going to assume that there is indeed a straight line that can separate your training set, and we'll remove this assumption later. But just to develop the algorithm, let's say we have a linearly separable training set. And so there's a sense that out of all the straight lines that separate the training set, maybe that straight line isn't such a good one. And that one actually isn't such a great one either. But maybe that line in the middle is a much better linear separator than the others, right? And one reason that when you and I look at it, this one seems best, is because this line is just further from the data. Right? That it separates the data with a greater distance between your positive and your negative examples and the decision boundary. Okay? And this second intuition, we'll come back to shortly, about this line, this final line that I drew being maybe the best line. This notion of distance from the training examples, this is the second intuition I want to convey, and we'll formalize it later when we talk about geometric margins of our classifiers. Okay? So, so in order to describe the support vector machine, unfortunately I'm going to have to pull a notation change. And unfortunately, it sort of wasn't possible to do logistic regression and support vector machines, and all the other algorithms using one completely consistent notation. And so I'm actually going to change the notation slightly for linear classifiers, and that'll actually make it much easier for us to. That'll make it much easier later today and in next week's lectures to actually talk about support vector machine. But the notation that I'm going to use for the rest of today and for most of next week will be that my labels y, instead of being 0, 1, there'll be -1 and +1. And right. In the development of the support vector machine, we will have a hypothesis Oh, right, and so, yeah. Okay. Now let's talk about. Let's see how much time I have. 15 minutes. Well, so I'm trying to decide how much to try to do in the last 15 minutes. Okay, so let's talk about the geometric margin. And so the geometric equals gamma I times W transpose W over norm of W. That's just equal to gamma times the norm of W, because W transpose W is the norm of W squared. And therefore, gamma is just transpose X plus E. Okay? And in other words, this little calculation just showed us that if you have a training example, xi, then the distance between xi and the separating hyperplane defined by the parameters w and b can be computed via this formula. Okay? So the last thing I want to do is actually take into account the sign of the correct classification of the training example. So I've been assuming that, you know, we've been classifying an example correctly. So more generally, define the geometric margin